Okay, this is 3.2, floating down the river, which is one of your teacher's favorite things to do in the world. I used to do a lot of whitewater rafting and whitewater kayaking, and miss those days. Anyway, here's the story. Alonzo, Maria, and Sierra were floating in inner tubes down a river, enjoying their day. Alonzo noticed that sometimes the water level was higher in some places than in others. Maria noticed that were times they seemed to be moving faster than at other times. Sierra laughed and said, "Math is everywhere." To learn more about the river, Alonzo and Maria collected data throughout the trip. So here we go. Okay, so look at this cool little table somebody just put on a piece of paper right here. So apparently Alonzo was on an inner tube and had a piece of paper and a pencil and was able to create a table. That's amazing. Anyway, here's Alonzo's table. And question number 1. Use the data collected by Alonzo. I misspelled Alonzo there. I'll fix that later. To interpret the key features of this relationship. Okay, here we go. Let's have some fun. So, I have given you a copy of this graph right here. And all we are going to do, if I want to talk about key features of a relationship, I like to look at a graph because then I can see everything clearly. So, we're going to take Alonzo's table right here, and we're going to plot these points on the graph that I have given you. So time is on the horizontal axis, up to 120 minutes, and depth in feet is on the vertical axis, f of x, depth in feet. All right, and I'm sorry, I grabbed a grid that I think went right to there, and I needed to add a few more columns here, so I kind of put this in. It's not perfect, but it's going to work great. So let's start plotting points. The input is 0, the output is 4. So it looks like 0's right there, and what? I scaled the f of x axis by 2, so my first point would be right there. And then at the 10-minute mark, we're at 6 feet. So here's 10, and here's 6. At the 20-minute mark, we're up to 8 feet. So at the 20-minute mark, that river is 8 feet deep. Nice job, Alonzo. And at the 30-minute mark, the river was 10 feet. It just keeps getting deeper. Boom. And then, look at this. At the 40-minute mark, we're back to 6 feet deep. So at 40, I'm going to go up to 6 again. And then at the 50-minute mark, I'm down to 5 feet. So 2, 4, 5 would be about right there. And then at the 60-minute mark, I'm down to 4 feet. So that's going to be right here. And at the 70-minute mark, I jump back up to 5 feet. Right here. And then at the 80-minute mark, I'm continuing to increase to 7 feet. 80 minutes. 6, 8, 7's going to be right there. And at the 90-minute mark, I'm at 12 feet deep. The river's getting deep. 12 feet right there. And then at the, where am I at now? 100-minute mark, I'm back down to 9 feet. So 2, 4, 6, 8, 9 feet, about right there. And then at the 110-minute mark, I'm at 6.5 feet. It's our first decimal right there. All right, let's do our best. 2, 4, 6, 7, 6.5 would be about right there. Oh, look at that. And then at the 120-minute mark, their 2-hour float down the river, they're at 5 feet. 2, 4, 5, right there. Now, think about this. Is this data continuous or discrete? Now, if you just look at the table, you might think, hey, this is discrete. My outputs are just whole numbers, every 10 minutes. But we're thinking about the depth of the water in a river as we're floating down the river. And isn't that depth going to change continuously? So what I'm going to do is just put a smooth curve through these scatter plots. And now, at these extrema, like here and here and here, I don't know if that's a max exactly at that time, but, so I just kind of roughed it out here. There it is. All right. Now, when I'm asked about key features, I'm only going to use the data I know. So even though my line went a little above the 10-foot mark here, I'm going to consider that an extrema, like that, that kind of stuff. All right. So anyway, with this graph now, I can do the key features of a function. And I'm going to give you a little chart right here that has everything throughout Module 3 that we are going to have to talk about when we look at the graph of a function. So the first thought is, and I just said the graph of a function, this is actually a relation right now, and we need to determine whether or not this relation is a function. And remember, to be a function, the relation, every input has to have one and only one output. Or we have to pass a vertical line test. Now, if I look at this graph carefully, is there anywhere that I can draw a vertical line that would cross that graph at more than one point? And the answer is no. So this is going to pass the vertical line test. Therefore, this is a function. Yes. And the domain. Now, this function is continuous. So I am simply talking about a domain would be interval notation for all of my x values in this graph, or t values if we're using time, t. All right? So I'm going to say x is in, and because x can equal 0, I'm going to start with a 0. And because x can equal 120, do you see that solid dot? I'm going to put 120. And this means that my domain is every x value from 0 to 120, including the endpoints 0 and 120. All right, so domain of a continuous function, we use interval notation just like that. Now the range. Now we haven't talked about the range yet, so this is new. But the range is simply the y values, the outputs. All right, and this is continuous, so we're still going to use interval notation. Now, what is my minimum y value in this graph? Well, I see it right here at 4 and 4. So my minimum y value is a 4. And what's my maximum y value? Well, I go all the way over to here. And I know my line went a little above that point, but that was not documented in the table. So I'm just going to use the value, the y value of this point right here, which would be 12. So the range of this function is from y equals 4 to 12. And y and f of x, remember, are the same thing. Okay, extrema. If they exist, that's ordered pairs. So I need the lowest point or points on this graph and the highest point or points on this graph. So, extrema. Well, that looks like a minimum value, and I need to write the coordinates of this point as an ordered pair. So when x is 0, f of 0 is 4. So that's the ordered pair, 0, 4. And then, now that's pretty high right there, but that's not an extrema. So let's go down here, and then I'm going right to there. Oh, that is also at the same height as this point here, so I better list this point too as an ordered pair, and the x is 60, and f of 60 equals 4. So that would be the ordered pair, 64. And then we increase, and we get to this max output right there. And again, I'll use the documented stuff in Alonso's table. So I'm going to use the coordinates of this point right here. And that's going to be, my x is well, that's 89, that's 90, and f of 90 is 12. So 90 and 12. Very cool. Now the intercepts, if they exist as ordered pairs again, intercepts would be, where does this function cross the y-axis or the x-axis. And I only see one intercept, and that would be this point right here. Oh, increasing. Oh, I skipped a spot here, so let's go back here a second. Okay, we found the extrema. Now I need the intervals where the graph is increasing. Okay, well, it looks like I'm increasing from here to there, and I'm talking about my x values, so that would be from 0 to this point right here, which is what, 30? And then I'm decreasing, and then I begin right here, I begin increasing again, and that's an x equals 60. And I'm increasing until I get to this x value right there, which is 90. So again, increasing and decreasing, we're talking about x intervals. All right, so I'm increasing from x equals 0 to 30 inclusive, and then from x equals 60 to 90 inclusive. That's why I use the brackets. Now, where is it decreasing? Well, I see two intervals where I'm going to be decreasing too, right here and then right over here. So the first interval would be from, and that's a 30 to 60, all right, inclusive. And then we go all the way over here from 90 to 120. Okay, so increasing and decreasing, we talk about the x intervals where the function is increasing or decreasing. Okay, now the intercepts, which I jumped to a second ago. And I did that because my points over here went so low there, and I thought, hey, we're right here. All right, anyway, intercepts. Well, again, there's only one intercept, and that's a y-intercept right there, so I need the ordered pair for this point. And that would be, well, the x is 0, and the y there is 4. And that is the y-intercept of this function. There is no x-intercept. Okay, now, f of 10 equals, this is function notation. So when x equals 10, right here, what is f of 10? That looks like a 6 to me. Oh, and I see it on the graph and on the table. 10, 6. Good. All right. And then f of what x value is 12? All right. Well, I got to go, what does y equals 12? I'm going to put probably a horizontal line right there. Did I do that? No, I didn't. Okay. Oh, and I'm at the wrong spot here. 12. That's all the way up here. Oh, I gotcha. So the y value of that point is 12. What's the x value there? That's a 90. So f of 90 is 12. Oh, I see it in the table too, 90, 12. There you go. So they're just having you use function notation for outputs and inputs. Now, when is this graph positive? That means when are all of my y values positive? Well, look at the table. Those are all positive. Look at the graph. The graph is above the x-axis. So this function is positive within its entire domain. So all I have to do right here is rewrite my domain, which you see that 0 to 120 inclusive. Guess what? 0 to 120. Because this graph is positive from x equals 0 all the way to x equals 120. When is it negative? Well, this graph never dips below the x-axis, so it is never negative, and we have notation for that. The empty set. That means there is never an x value where this graph has a negative output. And then for what values of x is f of x greater than 6? So now I'm going to go ahead and draw the horizontal line for f of x equals 6. There it is. And then I need to do the intervals where f of x is greater than 6 or above that horizontal line. Okay, now watch this. We equal 6 at this point, that point, and that point. So I'm going to use an open interval because I have to be bigger than 6. All right, so what is this x value right there? It's a 10. So I'm going to put a 10 right there. But there's a parenthesis because x or f of x equals 6 when x equals 10. And I need f of x to be greater than 6. So this is interval notation, but this is an open interval. This above, that's a closed interval. Know the difference. And that's going to go all the way to that x value, which is what? A 40. So in the open interval from 10 to 40, all right, f of x is greater than 6. Now, for the next interval, I put approximately because I don't know the exact values of that x value right there and that x value right there. So, I don't know. I just kind of, it's between 70 and 80. So, how about if I just go 75? Yep. And I'm between 110 and 120. How about I go 115? So, approximately the open interval from 75 to 115 minutes. In that open interval, f of x is greater than 6. These values are all greater than 6 right there. Now, that's it. Okay, let's do one more set of data for one of the other individuals floating down this river, and then we're done. Welcome to Features of Functions. Okay, so Maria created a graph by collecting data on a GPS unit. Wow, she's floating down the river on an inner tube with a GPS unit. That's pretty amazing. That told her the distance she had traveled over a period of time. So number 2, using the graph created by Maria, describe the key features, increasing, decreasing, domain, range, maximum, minimum, intercepts of this relationship. So first we need Maria's graph, and there it is. Nice job, Maria. And then we want our key features document where we can talk about everything. So our first thought is features of Maria's model. Well, is this a graph of a function? It looks to me like every input has one and only one output. This would definitely pass the vertical line test. So I'm going to say yes. And the domain. Well, the domain would be all of the x values on this graph, or you could call them time, t for minute if you wanted. All right. So we're going to start at 0. Notice I put a bracket because x can equal 0. And how far do we go? Over here to the right there. What is this x value right there? It looks like we're scaled by 10, so it's at 100, 110, 120. And x can equal 120, so I put a bracket on that side. Now the range. Those are all my y values. Well, my lowest y value here would be a 0. And y can equal 0. That's why we did a bracket. What is my highest y value? It's way up there. So what is that value right there? Well, let's see what we're scaled by. Is that 20, 40, 60, 80, 100,000? Or no. No. So that's 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000. That looks like 16,000. Yeah, there it is. Notice I didn't put a comma in 16,000. That would confuse people. So the range is in the closed interval from y equals 0 to 16,000. That is all of these values right there. And the domain is all of the x values from x equals 0 to x equals 120. Everything right there. Okay, extrema, if they exist as ordered pairs. Well, looks like we clearly have a min. And what are the coordinates? Well, that is x equals 0 and y equals 0. 0, 0. Okay, and then we have a max way up here. All right, let's write that as an ordered pair. So what is my x value of that point? Well, that was 120. And what's the y value? That was that 16,000 right there. 16,000. Now, when is this function increasing? It looks to me like it's increasing throughout its entire domain. It might be slightly horizontal right there, but again, she did this by hand. So we're going to assume it was just like, bam, right there just for an instant and then continue to increase. So we're going to call this increasing throughout its entire domain, which means I just list my x values again in interval notation. The domain was 0 to 120, and if this function is increasing throughout its entire domain, I'm just going to list from x equals 0 to 120 in interval notation. And again, this means the closed interval from 0 to 120. Decreasing. Well, this is never decreasing, so I'm going to put the empty set right there. And then the intercepts, if they exist as ordered pairs. So where does this graph cross the y-axis or the x-axis? And only at that one point, which is the origin, which is both an x and a y-intercept. So that point, as an ordered pair, would be when x equals 0, y equals 0. Now, what does f of 30 equal? Well, let's just go 10, 20, 30, and go to that point right there. What's that y value? That would be, wasn't that 2,000? 4,000. I wrote 4K right there. That's okay with you guys. Oh, now look at this. F of what number is 4,000? Well, wouldn't that just be my x value at that point? Which they gave it to me right there. It's a 30. And you look at that, yeah, f of 30 equals 4,000. All right, so now, when is this graph positive? Well, it starts at 0 and then is in positive. It's positive during the whole rest of the interval. So this is going to be a half open interval in interval notation. Now check this out. Notice how I did a parenthesis because at x equals 0, I am not positive. So that's open on the left, but then it's positive the rest of the way until we get to x equals 120, and that's why we put a bracket on the right. This is called the half open interval from 0 to 120. X can equal 120, but not 0 there. When is it negative? It's never negative. That's another empty set. And then for what values of x is f of x greater than 8,000? Well, let's just draw a horizontal line at 2,000, 4,000, 6,000, 8,000, right there. So when is f of x greater than that? Well, this, all right, I need that point right there. So let's think about this. I can't equal that x value because that's where we equal 8,000. F of x equals 8,000. So that x value is at, is that a 90? Notice the parenthesis and the 90. X cannot equal 90 because f of 90 equals 8,000. And then for the rest of the interval, all the way up to that x value right there, which was the 120. And that's a bracket on that side because x can equal 120. So again, we have another half open interval right here. All right. The half open interval from 90 to 120, where I'm open on the 90. All right, hope you're starting to pick this up. All right, number 3, this is part 2, interpreting data. Number 3, Sierra looked at the data collected by her two friends. So we have Alonso's graph, and actually Alonso created a table, and then we converted that table to a graph, and then this is Maria's graph right here. Anyway, so Sierra looked at the data collected by her two friends and made several of her own observations. Explain why you either agree or disagree with each observation made. So let's think of this as like, you know, Sierra is looking at this data right here and making these observations. Think about this as a test. How's she doing? And remember, she's floating down the river. She's just learning this stuff on key features. So don't judge. Let's just help her out. Okay, so A, the depth of the water increases and decreases throughout the 120 minutes of floating down the river. Well, if you look at our graph based upon Alonso's data, we're increasing, and then we're decreasing, and then we're increasing, and then we're decreasing. So that's a nice job, Sierra. We agree with part A. Part B, the distance traveled is always increasing. So distance traveled, that's Maria's distance graph right there. All right. And it looks like this is strictly increasing throughout its entire domain. So the distance traveled is always increasing. I can agree with that too. It looks like it might be horizontal just for a small interval, but we'll give you that. C, the distance traveled is a function of time. So, okay, well, yeah, look at how the graph is labeled. This is a distance on the vertical axis, so this measures distance traveled, and this is a function of time because time is on the horizontal axis right there. And this is also a function because it passes the vertical line test. Excuse me. So, Sierra, you are 3 for 3. Great job for somebody just learning this material. Part D. The distance traveled is greatest during the last 10 minutes of the trip than during any other 10-minute interval of time. Well, so the last 10 minutes of the trip, all right, the distance traveled went from, what was that, 14,000 feet to 16,000 feet. All right. Now, is there another interval where we traveled farther? Oh, look at from 100 to 110. Didn't we go from 10,000 feet to 14,000 feet in this 10-minute interval right there? So, Sierra, I'm sorry, we're going to have to disagree with this statement right here, and we're just going to verbalize our response right here. From the 100-minute mark to the 110-minute mark, we traveled 4,000 feet, while from the 110 to the 120-minute mark, we only traveled 2,000 feet. So, Sierra, you missed D, but that's okay. Keep trying. Now, E. The domain of the distance time graph is all real numbers. Well, let's see. The domain of the distance time graph is all real numbers. Well, Sierra, I would agree that we're talking real numbers from 0 to 120, but all real numbers would mean we'd be going forever to the left in a negative direction and forever to the right in a positive direction. So this is not all real numbers. This is only the real numbers from 0 to 120. So we have to disagree again. But you're doing great. Okay, how about F? The y-intercept of the depth of water over time function is 0, 0. The depth of water, the y-intercept is 0, 0. Well, here's my depth graph. All right. And that is a y-intercept of 0, 4. The y-intercept of the distance graph is 0, 0. So we're going to have to disagree again. So G. The distance traveled increases and decreases over time. Well, here's our distance. It looks like we already said that this is increasing throughout its entire domain. So the distance traveled is an increasing function. It's the depth function that increases and then decreases, increases and then decreases. So we're going to disagree again. The depth of the water is never 11 feet. Well, I know in the table, I don't think we ever saw an output of 11 feet, but we said that the depth of the water was a continuous function. Therefore, if there's a time where, like, right here we're at 10 feet, and then right there we're at 10 feet, and right here we're at 12 feet, so we must have been at 11 feet somewhere in between, so I'm going to disagree there too. The range of the distance time graph is from 0 to 15,000. Distance time, that's right here. Range, these are all these y values, and we're going from 0 all the way up to, and what's that value right there? Let me see, 10, 12, 14. That's 16,000 feet, and Sarah said we only went up to 15,000 feet, so we're going to disagree there too, Sierra. The domain of the depth of water with respect to time is from 0 to 120. So here, depth with respect to time from 0 to 120. We agree. My x min is 0. My x max is 120. That one worked. Good job, Sierra. The range of the depth of water over time is from 4 to 5. 4 to 5, that'd only be from here to there. And we're going all the way up to, it looks like at least 12 feet right there. So, got to disagree there, Sierra. I'm sorry. 2 more. Let's see how you do. The distance/time graph has no maximum value. I don't know. That looks like a maximum up there. Guys, that's definitely an extrema. I have to disagree again. And then the depth of water reached a maximum at 30 minutes. Depth maximum at 30 minutes. Okay, that's called a relative max. That is a peak right there. But we're talking about the deepest part of this river occurred actually at 90 minutes right there. So I'm going to have to say we got to disagree right there too. Okay, but again, Sarah, it's okay to be wrong. You're trying and you've made some really great statements right there. Keep up the hard work, and down the road, we're going to have you to a point where you can answer all of these by looking at graphs or tables.